So now we're ready to introduce thermodynamics. Thermodynamics is sort of the umbrella where thermal chemistry falls into. It's the study of the interconversion of heat and other kinds of energy. The laws that we get from thermodynamics are really useful because they help us understand the energetics and directions of certain processes and certain reactions. In this chapter, we're going to concentrate only on the first law of thermodynamics, which is based on the law of conservation of energy. And we've heard about the law of conservation of energy already in the first video. Just to remind you, it states that energy can only be converted from one form to another. It can't be created nor destroyed. So that's basically what the first law of thermodynamics is based on. In thermodynamics, we study the changes in the state of a system, and that's defined by the values of all relevant macroscopic properties. For example, the composition, the energy, the pressure, the volume, and the temperature of a system. All those variables, energy, pressure, volume, and temperature, are said to be state functions. Okay, and state functions I've defined here, it's the properties that are determined by the state of the system, regardless of how that condition was achieved. What I mean by that is that when the state of a system changes, the magnitude of change in any of those functions depends only on the initial and the final state. I have an example here where I'm showing two hikers and they're going up a mountain. And we see that hiker number one, the blue path, takes a much shorter route, and hiker number two, the red route, takes a much longer path. But it doesn't matter because they start at the same place and they end up in the same place. So that means that the potential energy, the gravitational potential energy of those two hikers are exactly the same. It does not matter that the path is different. That's what a state function is. All right, I don't care how you got there. I only care about your final and your initial state. So state functions, like I've mentioned before, are energy, pressure, volume, and temperature. The little triangle that you see in front of the variables, that's called delta. That means change. Okay, so a change in pressure is equal to the final pressure minus the initial pressure. So whenever you see that, don't get confused. Delta U is our symbol for internal energy. So what we're measuring is the change in the internal energy of a system between its initial state and its final state in a certain process. This internal energy basically has two components. It's got kinetic energy and potential energy. You can read in your book about the difference between kinetic and potential energy. I want you to note that it is impossible for us to measure all of these contributions of energy accurately. So we can't really calculate the total energy of a system with any real certainty. But the changes in the energy, those can be determined experimentally. But the other ones are pretty simple. Pressure, volume, temperature. You just basically have what the pressure starts at and what the pressure ends at, so on and so forth with the other variables. All right, let's move on. So here it is again, the first law of thermodynamics. It says energy can be converted from one form to another, but it can't be created or destroyed. Now we've told you that energy, the symbol for internal energy, is U. And we have also learned about systems and surroundings. Remember that if something is given off from a system, then the surroundings must take that up. Remember, that was the first video. So now let's put all of that together. If I know that energy is not created nor destroyed, then the amount of energy in the world must equal to zero. But I know that the equation on the left side must be whatever energy from the system plus the energy from the surroundings must equal to zero, because again, energy doesn't change, so it's equal to zero. But if I have that as my mathematical equation, now I can also say that whatever the energy of the system is, the energy of the surroundings, the change in the surroundings, must be the same but opposite in sign. Because remember, if the system gives off the energy, then the surroundings must take the energy in the same magnitude but different sign. So that is basically what that math equation is trying to say, which we know everything about that already. We're just putting a math equation to our words. So as an example, I have the combustion of C3H8. So propane is being reacted with 5 moles of oxygen gas. And this is a super exothermic chemical reaction. The chemical energy that's lost by the combustion equals the energy that's gained by the surroundings. So the transfer of energy from the system to the surroundings does not change the total energy of the universe. It basically just converts from the system to the surroundings. That is equal in magnitude but opposite in sign. In chemistry, we are normally interested in the energy changes associated with the system. So we concentrate from the view of the system. And I did mention that, I believe, in the last video. We don't really care about the surroundings too much. We care about the system. So I'm going to introduce to you a more useful law for us chemists. So here's another form of the first law of thermodynamics. This one is a lot more useful to us chemists because all we care about is the internal energy of the system. It states delta U is equal to Q plus W. First, we drop off the system subscript from the delta U because obviously we only care about the system. So we know that this has to do only with the system. So we don't have to discern it from the surroundings. So the internal energy of a system is equal to the sum of the heat exchange, that's Q, okay? So the heat exchange between the system and the surroundings, plus the work, which is W, the work that is done on or by the system. Now, I know this sounds a little confusing, but I'm telling you, this is really easy, so just stay with me. The sign conventions for Q, which is heat, and W, which is work. So the sign conventions for Q and W are Q is positive for an endothermic process. In other words, Q is positive if heat is being applied to the system. Remember, endothermic means that the system is taking up energy. So if you are providing heat to the system, then the Q is positive. If the process, on the other hand, is exothermic, like a combustion, that is a negative. Work is basically the same sort of concept. If the system is doing the work on the surroundings, then the work sign is negative. So if you're doing the work, you're the system and you're doing the work, that means that you started with a certain amount of work, but you've done work on the surroundings. So now when you finish, you've ended up with less work. So that means that your sign must be negative. And the opposite is true. If you're not doing anything, you're just sitting there, and the surroundings are doing work on you, then your work is positive because you haven't done anything. You just gained stuff. I'm going to go over this in a little bit more detail so you guys can visualize what I'm talking about. But again, it's really simple. The main thing here is that the internal energy of a system is equal to the sum of the heat and the work that's being provided on or by the system. And all you have to figure out is, in a word problem, is the system doing the work or is the system being provided the work? And again, is the system giving off heat or is the system taking in heat? That's all it is. All right, so let me do a little bit more visual example. To help visualize what I mean about these sign conventions, let's look a little bit more closely at work. So we have seen that work can be defined by force times distance. But in thermodynamics, it has a much broader meaning, which basically includes mechanical work, electrical work, surface work, all kinds of other work. But we're going to be concentrating on mechanical work. And a good way to study mechanical work is by showing the expansion and compression of a gas. Many of the processes we deal with basically involve gas volume changes, so it's a good way to study it. So the figure that I'm showing you shows a gas in a cylinder fitted with a weightless, frictionless, movable piston, okay, at a certain temperature, pressure, and volume. As it expands, the gas pushes the piston upward against a constant opposing external atmospheric pressure. So the work done by the gas to the surroundings is equal to negative P delta V. Okay, this is a new equation that you guys have never seen before. The minus sign in front of the pressure takes care of the sign convention for work, because remember, work and heat have those sign conventions. But before we go into that, let's look at how we derive this P delta V. We know from before that work is equal to force times distance. Well, pressure is basically defined as force per area. So basically force divided by d squared. Well, what's volume? Anything that's cubed. So d cubed would be the volume. So if you multiply those two together, guess what you get? Force times distance, which is equal to work. It's always good to know where these things come from. Another important thing I want you to notice is that work is not a state function, okay? I don't just want to know final minus initial in work. Okay, I want to know the path. So make sure that you remember that. The only things that are state functions are energy, pressure, volume, and temperature. Work is not one of them. So here, to figure out what the work is, all we have to do is look at what's going on. You start out with a gas cylinder that has a certain amount of volume and a certain amount, of external opposing pressure. But the final state of that is that now the system has expanded. Okay, so the volume change is greater than 0, right? So let's say it started at 0 and now it's bigger, so now it's greater than 0. Because the change in volume is greater than 0, that means that the system has done the work to expand against the surroundings. So that means that work must be negative. So the sign convention for this would be the negative sign, because the system has done work onto the surroundings. So it should be very simple for you to understand. Let's try a problem. One thing I do want to point out is, again, work is equal to negative P times delta V. That P is the external opposing pressure. But if the pressure is 0, for example, if the gas is expanding against a vacuum, right, there's no pressure, then the work done must be 0. Right? Because work is equal to negative P delta V. But if there's no P, if the P is 0, then that whole work must be 0 as well. So I just want to point that out. All right, so a certain gas expands in volume from 2 liters to 6 liters at constant temperature. Calculate the work done by the gas if it expands against a vacuum. Well, we just talked about that. If it's against the vacuum, that means that there's no opposing external pressure. That means that P must be 0. If P is 0, then 0 times whatever is still 0. So work done is 0. All right, so calculate the work done by the gas if it expands against a constant pressure of 1.2 atm. Well, the external opposing pressure is 1.2 atm. So we write W is equal to negative P delta V, negative P. So P is 1.2 atm. Times the change in volume. Well, the change in volume is, it starts at 2, ends at 6. So final minus initial, 6 minus 2 liters, which ends up being negative 4.8 liter ATM. Liter ATM is a new unit that we've never seen before, but we can express liter ATMs in the form of energy, or the units of energy, which is joules. So 1 liter ATM is equal to 101.3 joules. So basically what we do is we convert our answer, negative 4.8 liter ATMs. We set up a conversion. 1 liter ATM is the same as 101.3 joules, and that gives us negative 4.9 times 10 to the second joules. Now, check this out, okay? So this is how you check your answers. Because this is a gas expansion, that means that the system has done work onto the surroundings. So if that's the case, then the sign convention of work must be negative, and it is. That's why it is negative, because the gas is doing the work on the surroundings, and that's why the work done has a negative sign. All right, that's it for this video. I am going to do some more problems maybe like these in the next video, but we have to start talking about enthalpy of chemical reactions. All right, see you later.